Okay, so we're going to talk about the analog to digital converter for our STM32 microcontroller, and specifically we're going to try to talk to it related to the lab. Okay, so first off we're going to start a little bit talking about just analog to digital conversion process in the first place. I will probably go through more details with a separate analog to digital conversion video, but what I try to do with this set of videos is just mainly try to cover and convert two into one that primarily is for the lab. So anyways, we'll talk about the analog to digital converters. We've seen this sort of block diagram approach of of our microcontroller before, and we've done the GPIO ports, we talked about that stuff. Now we're going to specifically talk about the analog to digital converter. Specifically we're going to talk about fundamental concepts related to it, the system description, and then later on we're going to talk about the registers and programming that we will need to get data from the analog to digital converter. Obviously you can expect in the future we're going to talk about the timers, and we may talk a little bit about the serial port communications right there too. Okay, so there's a couple of things that we have to be aware of. We've done a little bit of this before. I mean, again, we're still using the GPIO pins because we are using the input-output ports of the microcontroller, but specifically we're going to tie them to the analog to digital converter. Now, how do we do that? I mean, this is the same kind of setup that we had before, right? We talked about the joystick being hooked up to the different LEDs and the different buttons of the joystick. Well, that was when we were considering everything either to be a digital input for the joystick buttons or a digital output for the LEDs. But what about the other things that we have? We really haven't talked about the alternate function or the analog. Okay, well, obviously we're going to try to get some analog signal. We're going to convert it to a digital signal, so you can guess that, hey, what we're using is we're going to use the analog input of a pin. So specifically we're going to set the pin for whatever GPIO port that we want to do. We're going to set the motor register to 1-1 to have it enabled as an analog input. Okay. A couple things about the A to D conversion. We can have up to 12-bit successive approximation. Actually, I think in the STM32 it may be 16-bit. Anyways, that's the successive approximation, and then it says, okay, we can get 2 megahertz conversion rate. In other words, we can do 2 million conversions in a second. The A to D conversion range, it says here, is 0 to 3.3 volts. That may be a little off. That's as long as you're using the standard reference voltages of everything. That's what the analog to digital converter can do, because normally the reference voltage is ground and the upper reference voltage, the high voltage, is 3.3. So anyways, that's sort of the idea behind that. For the A to D converters, we have a number of channels, and we can do a single channel conversion, which it says there is a single sample conversion at one particular time instant, or we can do continuous conversions, and that means you convert, then you can read it they convert again, and it constantly is doing this conversion process. So it says non-stop sample collection and conversion. We can also do discontinuous conversion, so we can do sequential conversion of some channels in a group. The book talks a lot about injected channels and so forth, and that's like a group of channels that are together, but you can also create your own channel group itself that you have in the regular channel setup. Scan conversion, you can have sequential sampling and converting of an array of channels one after the other. So we'll get to another slide, but I think the importance of this is you can do like a single channel, or you can do a series of channels. You can do that one time, or you can do it continuously. So there's a path you can do it. And I don't know, microcontrollers are not my expertise area, but if you look at like the old Freescale boards that we used to use a long time ago, they also did this like grouping of A to D stuff in channels. So I think that this ARM microcontroller was sort of done with that in mind. I'm sure to try to make it so you could easily put in place these ARM microcontrollers in places that those Freescale ones were used. So anyways, if we wanted to set, for example, PA2 to the analog mode, then we would need to come in here and set the motor register. Remember, this is pin PA0 if we did it. This is 1, this is 2, so we would need to put a 1, 1 in those 2 bits. And we know the process of going through to actually have that implemented. Okay, this is actually a slide from the old Freescale book. I think it's a good slide though, because it sort of gives an idea of something that this book does not really do a good job of. And it's trying to say, look, we live in an analog world. Now, how we get something from an analog signal, which could be pressure, temperature, light intensity, sound, whatever, how do we get that into a voltage? So something has to happen to do that. So we have to have some sensor that takes this physical variable into a raw voltage that then has to go through some manipulation maybe to get a compatible voltage for our board, and then this compatible voltage that's allowed to go into our board and be interpreted by the analog to digital converter into a binary number. And okay, what this talk is talking about right here is we have to have some sort of transducer interface such that, we can have, it calls it VRH and VRL. In our book right now, you typically see this as just VR, VREF, and then the low voltage would be just ground. So basically what we're saying here is we have to have some transducer interface that gets this between, we might think of it between 0 and 3.3 volts for the compatible voltage that would go into the microcontroller. But the raw voltage here, it could be something from -15 to -2. You don't know, but somehow you're going to have this transducer interface that takes this -15 to 0 and takes this -2 to -3.3. Or you're going to have the ability to change those levels in the board or the A to D conversion so that this is considered the high and this is considered the low. Well, I did it backwards since I used negative numbers there, but this one would be considered the low and this would be considered the high. There's some that could do that, but you have to have a way to get the raw voltage into something that the computer can easily see. So this is just trying to show what you might do for that example. So here it's trying to show that you have some transducer that gives you some signals that have X1 and X2, and they'll produce these minimum and maximum voltages. Well, you can pass that through an amplifier and an offsetter so that those can become this V2 max and V2 min. And just to make it clear, that's what I was sort of saying right here. Those are those voltages that can easily be interpreted and put into the microcontroller A to D system. So this is sort of like, you know, the filter is going through here. Then we have to scale, and then we have to offset. And so scale can be an amplifier, offset is shifting basically. So that's how you can get that, and that's what it's sort of showing right here. Here's the scale factor, and here's the offset. And if you know what your V2 max and your V2 min are, and you know what your V1 max and V1 min are, then you can solve for the K and the V. So here's what it's trying to show you. What if your V1 max and V1 min are 300 millivolts and minus 100 millivolts, and you want it to be standard TTL output, so 5 volts is the highest, 0 volts is the lowest, then that would give you that K needs to be 12.5 and B needs to be 1.5, and that's what you have to put. You have to put an amplifier and offsetter in between here and your microcontroller system to be able to get the proper readings there. So for the big picture, again, we've got these voltages that are the low level, between the low level and the high level for our analog signal, and we've got to convert that into some digital value. And so you see that what it's trying to show you is, okay, at these little instants in time, I'm going to take a sample and I'm going to set that up as a voltage, as a binary number, that if I then converted back into a voltage, this analog signal that did look like this will look like this. It gets sort of set at that DC value for whatever that binary volt value turned to a voltage was from the A to D to converter, and then converted back, and then it's done for some sampling period right there. So that this TS is the sampling rate. The encoding is, you know, we sample that signal at a specific instant in time, and we have to encode it into the binary variable. How many bits are we going to use for that encoding? And then it says the quantizing and resolution. Well, that's how many bits, and the resolution is determined by how many bits you pick. And then quantizing basically says how many levels you're going to have. It's also sort of determined by the bits. And then the data rate is basically, okay, how many bits times the sampling rate in some sense, because you have to know how many samples you need and then how many bits per sample. So this is just trying to show you that you're going to discretize both in the time domain as well as the voltage domain. Just as a general overview, obviously, one thing that we would have to be concerned with is sampling rate. You might say, okay, well, we'd like to sample as fast as possible. Well, okay, that generally sounds true, but if you know that you're not going to have a signal that varies very quickly, then you're going to end up having way more samples. And then if each sample, you know, takes a large number of bits, then you're going to end up having a huge sort of data flow that may not be exactly what you need. So you want to have this optimal sampling rate that shows you how fast you need to sample, but not really any faster than that. This sort of comes from an analysis that you will see possibly in 331, but it's coming from Shannon sampling theorem and the Nyquist criterion. You'll definitely probably talk about it, if not in 331, in communications. But it basically says that you need to sample the signal at the minimum frequency of twice the highest frequency content of the sampled signal. So For example, we typically hear up to about 20 kilohertz. So if you look at it, CDs are sampled around 44 kilohertz. In other words, double the audio frequency and a little bit more to give a little bit of headroom for it. So if you know the sampling frequency, in that case you would need to have the sampling frequency be at least 40 kilohertz, then you know the time interval between the samples TS that we talked about on this previous slide. Now, the whole point of doing that is if you then go back and try to get the analog signal from the sampled signal, then if you have a low-pass filter and you set a brick wall low-pass filter that can cut off, you know, if you think of this as some high frequency where it cuts off everything up to that frequency passes, everything past that frequency gets cut off completely, then you can end up getting a replica of the analog signal. So somehow it seems strange that you can make this into a binary / digital looking signal, but yet at the same time you get the original analog signal back from it. And anyways, there's the theory there that you can see, as long as you can do impulse train sampling that is perfect, it would indeed give you that. So anyways, here's another example that says the phone company samples human voice at 8 kilohertz and then uses a 4 kilohertz low-pass filter to prevent aliasing. Again, that's because while music is typically requiring higher frequency range, for our standard voice, you're going to be limited to about 4 kilohertz. Obviously, you can sing higher than that, but for typical telephony, that's good. And then, of course, the telephone is old by your standards now, but that was something that they could easily do and then discretize at that time and not have an overwhelming system in terms of the data rate and all that sort of stuff. Okay. So, one of the things that you need to talk about when you're looking at this is the encoding process. Now, this is showing the example if VRL was 0 and VRH is 5. And specifically, you can see we have B in this case is 3. We're doing a 3-bit binary encoding, so that gives us 8 or 2 to the 3 different levels. So you'll see the 0 level, here's the 1 level, 2, 3, 4, 5, 6, 7, 8 would be there. Now notice one thing with this particular setup, would we ever, if this was our setup and VRH was 5, would we ever get 5 volts out of our analog to digital converter? No. Nope. We'd get, if this was our setup right here and we did it this way, which is a linear encoding, it shows you the highest that you would expect to get is 4.375 if we were going from 0 to 5. So just be aware of that. You're never going to get your high voltage because you basically are saying you have 1, 2, 3, 4, 5, 6, 7, 8 segments there. So you can't encode the whole range like that because we only have 8 different segments. So it could be that I could make the 8th one be right here, but then if I did that, then the lowest one would be right there and not it be at 0. So you realize there's a trade-off that you're going to have with this encoding process. So the quantization, resolution, and the data rate of our A to D converter goes as follows. Quantization basically tells the number of discrete levels the analog signal is divided into between VRH and VRL, and it says more levels provide better representation of the sampled signal. You could see that we have 8 levels there. So our resolution here is the voltage per step. And so that's VRH minus VRL over 2 to the B. Well, that's this 0.625 volts right there in this case. So that in this case is 5 minus 0 over 2 to the 3, so 8. So 5/8, oops, sorry, went the wrong way, is that 0.625. Now, what happens if we want to change to a different level? What if it's 256? How many bits? Well, if 3 bits is 8, 4 bits is 16, 5 bits is 64, 6 bits is 128, 7 bits. Did I do that right? I think I'm messed up. 3 bits is 8, 4 bits is 16, 5 bits is 32, 6 bits is 64, 7 bits is 128, and 8 bits, which is what I knew, is 256. So you would have to have 8-bit conversion if you wanted 256 levels. And our data rate basically is, you can see here, it's that sampling frequency that we had times the number of bits per sample. So that tells you the data rate that you would have. Okay, this is a figure from our book, actually, and it talks about the analog to digital converter. And it tells us a little bit about what has to happen here. And the idea of the electronics part of this is not all that important, but it does give us, some knowledge that we need here. We have this input voltage that we're going to sample, and you can see what happens when we switch this switch down here. We're going to allow this voltage to come in here to the op amp, and this capacitance is just going to allow that to charge to that voltage. That's all that's really going on here. Then this gets put over here, this sample gets compared to a value on the DAC. And it basically gets continuously or successively approximated in this comparator to where we get, shows this control logic to where we get this actual value for our output. And I'll go through an example on the next slide, I believe it is, that talks about this. But basically we have to think about this rather simply as, okay, we're going to bring in the input voltage. It's got to be sampled, so there's got to be some level of time that it takes this capacitance to charge to the level. It's got to be there. Then we sample it, and then we go through this approximation procedure to where we find that digital value for the analog that has come into that. And how this is done is through this comparator and this control logic. So here's what we have going on in this example. And you can see what's happening right here is, okay, here's where the voltage is being sampled, and it's sampling, and we have to take some sort of conversion time, and it has to settle. So we don't want to settle until that capacitance is charged to that level, or we get the wrong value. Okay, now what we get, once we get here and can sample, the first thing it does is it changes the most significant bit as it goes into the comparator. Okay, let's just go back to this. Okay, we change the most significant bit in this slide right here. Okay, that's this bit. And what does that mean? Okay, we're going to compare to 2.5. Okay, let's say, for example, this value, it's supposed to be, you can see the value was 0.69. That's what our analog value is, and we want to convert it. So it's saying our maximum is just 1. Okay, so let's just say we want to try to make this comparison. Okay, oops, I keep going the wrong way. So we want to compare this, and that's 2.5, but that maximum is 5. So we need to divide it by 5. And so we know that first value will be half, which makes sense. Okay, we're basically saying, okay, here's half. We're going to compare the number to a half. So that's what we did. Now notice, this is actually going to convert into 4 bits. So we're not just doing 8. Our quantization is not 8, but the idea follows from that previous graph. Okay, so this bit is going to represent a half a volt. We take that in and we compare the sample to a half of a volt. So if we've set up the DAC and it's converted 100, that means 5 volts is right here. So the sample is being compared, no, it's 5. The sample is compared to half. That's what the comparator does. And if it's higher than a half, then we know that first digit is definitely a 1. If it's lower than a half, then we know that first digit, or most significant digit, is a 0. Okay, so that first time it was higher. So we know that first digit is a 1 because right here we checked 0.687 is bigger than 0.5. Okay, so then what do? We change this next most significant bit and we put a 1 on it. Okay, when we do that, that's going to make 0.5, and then that next increment is half of that, so that's going to be 0.5 plus 0.25, so that voltage is 0.75, and so that's what is run so that this time what's run through that DAC is 1100, so now we get 0.75, and then the sample is compared to 0.75. Okay, the sample is not bigger than 0.75 because right, it's 0.687. So then it knows, the analog to digital converters knows the second bit is not a 1, but it's a 0. Okay, so it knows that second bit. So then the process is go to the next bit. And that next bit, it puts it a 1. Now we know the first 2 bits are 1 and 0, you know, from most significant to least significant I'm talking about here. So then we'll put a 1 on this next to last bit, and that voltage would be 0.5 plus, okay, this digit was, the first digit was the 0.5, this one was the 0.25, so this is the 0.125. So 0.5 plus 0.125 is 0.625, so you can see that corresponds to this level right here. So this 0.625 volts is that value bigger or less than the sample? Well, again, right, this value is less than the sample, so what does that mean? It means that that 1 is correct for that bit. So now we know the next 3 bits. We know that the next 3 bits. We now know that those 3 bits right here okay, for some reason my pen has stopped writing. Don't know. Let me stop it. So now we know these 3 bits right here are 101. Again, we'll go ahead and guess that this last bit is 1 and see what happens. Okay, so we talked about this being 0.125 for the third bit, so the lowest bit is the 0.0625, and again, that corresponds to the the quantization error could be 0.0625 if we look at that. And so then we have 0.5 plus 0.125 plus 0.0625. That's what this voltage level is right here, and that's 0.687. And so then we say, okay, is that voltage over here, which again, this is basically coming over here and saying 1011, which is 0.5, 0.0 or 0.125, and then 0.0625. So we're adding those. That goes and gets compared to the sample. So that value is 0.687. The sample value is 0.69. Is the sample value greater than 0.687? Yes. So that means this last bit is a 1. Now, if it turned out that the sample was down here, let's say at 0.68, then we would say, no, it's not. So that last bit would have been a 0 in that case. But since 0.69 is bigger than 0.687, then that last bit is a 1. We've gone through 4 tests, and so our analog to digital converter after conversion would give us 1011 as our conversion. Now notice, if we want to convert into 4 bits, how many processes in that successive approximation converter does it take? 4. The first time gets our first bit, then our second bit, then our third bit, and then our 4th bit, and we're done. So if we have an 8-bit successive approximation converter, how many times does it take to go through it? Well, 8. You have to go through this process for each bit. Now this is for the successive approximation converter. I'll talk a little bit in the analog to digital converter chapter lecture about the other types, but this one is what, I don't really need to discuss any more than the one that is used here. So that's what the STM32 uses. So if you have your STM32 set up to make 12-bit conversions, then it's going to take 12 cycles of that successive approximation converter. Okay, so this is just giving a few examples and talking about what might happen. It says the spectrum of an analog signal is 200 to 3.9 kilohertz, a rate of 10,000 samples per second. And you say, okay, is this adequate to allow reconstruction? Well, the first thing is you should just look at the high frequency. It's 3.9 kilohertz. What's double that? Double that is 7.8 kilohertz. So we need to make sure we have 7,800 samples per second or higher if we want to be able to do it appropriately. We have, so yes. Analog conversion, it says, yields a 10-bit binary value. And it says, okay, well, we just discovered that 8-bit is 256 levels, so 9-bit is 512 levels, 10-bit is 1024 levels. And then, okay, if that's the case, and our VRH is 5 and our VRL is 0, then what is 5 over 1024? It's 4.88 millivolts. So that just shows the resolution that you would have for the the analog to digital conversion. Okay, so, and that's, what is that basically telling you? That tells you what that lowest bit, what that difference is going to be. For that lowest bit being a 0 or a 1. Okay, the next example says, well, what if we wanted to convert this 3.97 volts into a binary number? And we wanted to use this quantization and so forth that we talked about right here. And then we're going to talk about, well, what happens if we want to calculate the data rate after that. Well, if we have 3.97 volts and we convert it to a binary number, we can see that 3.97 divided by this 4.88 millivolts would give us 813.5. Okay, this is not an integer number. We know if we're going to have 1024 levels, we need an integer number of one of those 1024. So what is that going to be? Well, okay, here's a choice that you might have to make. Should we choose to round up? Should we choose to round down? Should we choose whatever? Well, you saw in the previous case, that's all, we're never going to get to the maximum, so we use the floor function there, and so we're rounding down to 813, and then this is the binary representation of 813. So that is the number that we would see on the data register of the analog to digital converter if we convert it. Okay, now the last thing that it shows here is, well, what would our data rate be if this was our whole process? If we used 10,000 samples per second, we use this quantization of a 10-bit number, and we used these voltage levels for VRL and VRH, then we would have 10,000 samples per second, because that's how many times we're sampling, and our data rate is, we're going to have 10 bits per sample. So our data rate is, and that 10 bits per sample is just chosen right there, but that would give us a data rate of 0.1 megabits per second. So to give you an idea of these numbers, you know, at 1.1 megabits per second would have been pretty fast, but with these new HDMI 2.1 cables that are having to support up to 8K TV with audio, I think the data rate is like 48 gigabits per second if you max it out. So anyways, this is a relatively low bit rate for this particular one. Okay, so the next spot is, what are we going to do with our onboard analog to digital converter? How are we going to control all this? What are our registers that we need to look at? And so forth. Okay, we already know we need to set up the GPIO pins. We already talked about that. We have to set them up for analog mode. And so the other thing we have to do is say, hey, on our board, what pins can we even use? And so, because this is a strange thing about this board, we know that the STM32 has 3 sets of analog to digital converters. But that's on the chip. Do we have access to every one of the pins on the chip? Well, I guess maybe if you go attached to the pin on the chip directly, maybe yes. But what about our board? Where does our board have pins that we can easily access, you know, those pins on the sides of the board? Where do those pins give easy access to pins that are tied also internally to the analog to digital converter board? Well, here, this is what it shows us right here. We have easy access. Here it shows us to where the channels are. They're tied to, you know, GPIO port C0 for the first channel, C1 for the second channel. Now, all these are on the first analog to digital converter, but ADC1 on has 16 channels that we have access to. You can see it right here. There's the 16 channels, and there is the channel 0 that's got the reference, and here's, you can see the internal temperature and the battery. so forth for those. So we have access to the 16 channels. But specifically highlighted in this box are our analog to digital converter 1 channels that are easily accessed by our pins on our board. So channels 5, 6, 7, and 8 of ADC1 are also tied to port A0, port A1, port A2, port A3, and then 10 is on port A5. So we have access to those, and you can see here whether or not they're on, it says fast channel or slow channel. So 5, 6, 7, and 8, where are those? You can see the slow channels are here. So if you want to do fast, you have really 5 and 6 that you can use. The rest are sort of on the slower channel. Anyways, you also see this channel selection switch, which basically says what's going on. Here you see the successive approximation for the analog to digital converter. And we have the reference voltages VREF plus and VREF minus, which are typically already defined and hooked up on our board. So anyways, it's one thing to point out, it's not that you don't have tons of analog to digital channels available to you. You do. But for easy access to pins on the board, you don't have nearly as many as you might like. Okay, we've already talked about this, what's connected to a pin and so forth, but notice here is the mode that we're taking for that GPIO pin. We're taking it as an input in here, and we're taking it as an analog input. So that means it's not going to go through this hysteresis curve, we're not going to do any alternate functions, and we're not doing, obviously, any treating it as a binary bit or anything like that. Okay, so now let's start talking about what we're going to do to set up the pins and the port and the conversion process. So again, we need to set the motor register to pin 1-1 because we want it to be the analog mode of that GPIO port. So for us specifically, we're going to do this 12-bit successive approximation. So notice that 10-bit we just talked about was 1024. 12-bit is going to be 2 to the 2 or 4 times higher than that. So that's going to be 4 times 1024 or 4096. So our standard that you're going to see in your template file is you're going to see something that will give you the idea that you have 4096 levels in there. So be aware of that. We have the up to 2 megahertz conversion rate for the way we set up the clocks. The conversion range, the way it's set up, is going to be 0 to 3.3, which is a sort of standard. It's not TTL 0 to 5, but it's a second standard below that. Okay, we can do a single conversion for one conversion in a single instance. We can do continuous conversions on a single channel so that it does that conversion over and over. We can do, it says here, discontinuous conversion, which means sequential conversion of some channels. So that's sort of saying you're doing a bunch of channels but just a single time for the conversion. Or scan conversion, which means sequential sampling and converting of an array of channels one after the other. So this is like scanning and continuous sort of, so multiple and continuous conversion at one time. So this particular one says, okay, if we put this in our motor port 3 right here, those last 2 bits are going to be 1, 1. So this is looking like it's setting port A0 to be analog mode. Well, remember, that's what we were wanting right there. Now that's connected. Remember, got to make sure in your head you're correcting this right. Port A0 setting as analog input is going to be referencing the channel 5 for the analog to digital converter. Okay, the next step it says here is to set the analog switch control register. There's one thing that's sort of important here, and it says this connects the analog line for the port to the analog to digital control system. It's an extra protection layer since the analog to digital converter inputs are extremely sensitive. Obviously, by default, since you're trying to use such small difference levels, I mean, it was just 4.88 millivolts, so it's 4 times smaller than that, about a millivolt. If we looked at the levels that we had for the previous, with the previous reference voltages, then what does that tell us? It tells us that it needs to be quite sensitive. So that means that you can, have an easy ability, if you're not careful, to fry the chips. We used to actually do this analog to digital conversion with some chips that we would have externally, sort of like the decoders that you all use for the BCD decoder section. And for that, we actually tied it into the Freescale Motorola boards. And one of the big problems is we had a pretty nice setup, so you could do the next, the Etch-a-Sketch lab, which we'll get to, and it would look all good and nice. The problem was, so many times people hooked up those things incorrectly, and it was about a $20 chip. Just the analog to digital converter chip. That's it. That's all it did. So anyways, they're expensive because when you get high bit conversion, then obviously you're trying to be quite precise. Anyways, what we have to do is we have to go and I don't have that anywhere here, but basically we're having to select the analog switch to allow that analog input to actually get into the analog to digital converter. Okay, so it says here we're activating port 0, which is ADC 5. So there it is, we're putting in this GPIO A. So GPIO port, the analog switch control register, is going to have 1 in it. And that's, so we're putting 1 right there in that bit, and that's basically going to activate port A0. And now this is going to be our ADC, analog to digital converter input 5. And you can see what it says here is it says if there's a 0 there, it's going to disconnect the analog switch to the ADC input, which is what it would be by default. 1, it's going to connect the analog switch. So if you don't connect the switch, then the value that you have at that input is not going to get to the ADC converter. And notice it says only the I/O which connect to the ADC input are effective. Other I/Os must keep their reset value. Okay, so now what about the rest of the analog to digital system? So we've talked about what has to be done to the port. We have to set the motor register right, and we have to set the analog switch control register to be tied into the analog to digital converter. Now what about the A/D system just in general? Okay, it says here for our A/D system there are 3 analog to digital converters, and they share the same 16 input pins and clock. So that's just so you don't have to, obviously have 16 pins for each one of them. We're trying to be careful with how many pins and everything we have. So For us, though, we're only going to deal with ADC 1. Obviously, it doesn't really make a difference if we deal with the others, but let's go through and see how we need to set that up. There's a couple of things here that are sort of important that maybe we'll go over a little bit more. Here's this J stuff. You might say, what's that? That's the injected channels. We're not really going to use those. But that is what they're there, and I'll talk a little bit more about them when we do that chapter of the book. Here's the analog watchdog 1, 2, and 3. What's that? Well, that's talking about if you have a voltage that's higher than the high reference voltage or lower than the low reference voltage, that can that can select like the watchdog, which can then run an interrupt that says, oh, something's going on. Because most of the time that means, hey, I've got an analog input that I completely didn't expect to get. Something is going wrong in the system. So you have a way to execute something based upon that. You can see other things with the ones that we're going to do here. We have to have our sequence register and all this sort of stuff that we'll talk about. This is, notice it's tied into this. There's our successive approximation analog to digital converter, and then it's going to whatever we want to do for our outputs. And you can see some of that stuff is going on there, and here's like other things, here's interrupts, so forth. We have lots of different things, but I talked about the main ones, and then we'll talk about this stuff here in a little bit more detail. So the first thing that we have to do, just like our GPIO ports, we had to turn on the clock. We have to turn on the analog to digital clock. So that's right here. Now you're going to see this in your template, and basically this is, you can see this is the analog to digital converter channel enable. Well, okay. This looks confusing, but again, it is in that startup file, and if you look under the analog to digital conversion, section of that startup file, you're going to see that this ADCEN sets a bit to start just like anything else. It's like setting bits in this register, but it's setting a bit that basically says, okay, start the clock. Okay, so this is the same type there. So you're starting the clock, and then you have to take the analog to digital converter out of its power down mode. And if you turn it on and you've just turned it on via the USB port, it should be in the power down mode. In fact, one of the things that was sort of weird with my firmware in the first place is it started out in a power down mode before I updated it, that you couldn't even get it to wake those up. I don't know. I had to do that special setup that it requested from the author's website. Anyways, you have to take it out of that deep power mode, and you might ask yourself, why is it in that deep power mode in the first place? Well, it's in that deep power mode basically to save power. These analog to digital converters, by doing this, changing voltages and all that sort of stuff in this comparison, you're actually running a part of the overall microcontroller that's pretty power intense compared to other things. So if you're not using it, you better turn it off so that you can, not expend the power related to that. So here it is. It says, by default, the analog to digital converter is in the deep power down mode, where its supply is internally switched off to reduce the leakage currents. It says the reset state of bit deep power down is 1 in the ADC X. So X is whichever one you're using. So ADC 1, CR register for us. So it says to start these operations, it is first needed to exit deep power mode by setting that bit to 0. And notice that bit is right there. So by default, it's 1, and it needs to be set to 0. It says, then it is mandatory to enable the analog to digital converter internal voltage regulator by setting ADV REGN, so enabling the voltage regulator for the analog to digital converter, and that's this bit. So you got to make that 1. So notice it's a little bit backwards. You're putting this 0, but putting this 1. Both of them are in this register right here is the ADCX underscore CR. So this analog to digital control register is obviously doing a lot for us there. You might guess that it's also going to tell us when the conversion and so forth is done. Okay, so it says the software must wait for the startup time of the ADC voltage regulator before launching. In other words, as you can imagine, you turn on the analog to digital converter. It's been in a deep power down state, and then you enable the voltage regulator. It takes a little bit of time before those get ready, and you can start actually doing a conversion that you can trust. And if you don't wait that length of time, then you can't trust the results. So you'll see basically a generic while loop to get rid of us having, to be in trouble for that. Okay, so it says, okay, let's turn it on. So at first we need to set deep power down to 0. So what do you see? You're ANDing. Okay, what we've basically done here is we've set this last byte, or this last set of 4 bits there to 0, 0, 1, 0, or 2. So we've ANDed with the complement of that. So that means everything was 1s and only bit 29 was a 0, because we did this complementation like we've been doing. So what did we do? We made that a 0, which means taking it out of deep power down mode. And then, okay, we've enabled the regulator by doing the OR function. So we did the OR function. We put 0s in those 3 and a 1 in this. So this is that. So notice, this one is going for those 4. This one is going for those 4, and so forth. So this last hexadecimal is going for those highest 4 bits, and that's all we've done. So by doing this, then we've turned on the clock. Now what you'll see most of the time is, rather than see this number here and see this number here, they're going to use these as sort of this ADVREGEN as a variable, and this deep PWD as a variable, so that you don't have to remember which way it is. I sort of think that's a little bit silly, but at the same time, they use these variables and all over the place, so you need to sort of be aware of that. Okay, so now that we've turned on and we've waited for the regulator and everything to settle down, we need to select the clock mode for the analog to digital converter. And the clock can be configured a number of different ways. In fact, if you look, the author has a video on his website that talks a ton about, it's like a 10 to 15 minute video, I think, on just selecting the clock. That's not that big of a deal for us, but it is important to know that you need to do it. So it says you can set it from the internal clock to an external input from something else. So like you could get a timer from the board that is tied into the clock for the analog to digital converter. Now it says this will set it to the master clock on the system at 16 megahertz. And so we're setting the capture control register here to this. And we'll talk about this a little bit more when I look at the analog to digital control chapter, because we could, use this 216 megahertz, and we could then pre-scale it by a specific value. That's sort of what that video by Dr. Zhu talks about. But you can pre-scale it to get a lower value for the ADC clock if you want to. And so this common control register, that's what this is talking about, is going to allow us to use a prescaler if we want. I think it's 3 bits within that common control register that control this prescaler, because I think it can go from 0 to 7. So then we need to, once we've set the clock, then we can actually do a conversion. So these are the 4 different conversion types that we talked about. So single channel, single conversion, single channel continuous conversion, multiple channels single conversion, multiple channels continuous conversion. Not really any big difference in the idea of what you would need to do, but obviously you need to know where the different results are going to be. We didn't really talk about the injected channels, but one of the nice thing about injected channels is that each injected channel has its own data register. Whereas for us, if we're using our standard channels, then we have to use the same data register for all of those channels. So you need to make sure if a conversion has been done, you read the data from that data register, or you can end up not reading the right thing. So anyways, it says, so here's the injected channels that we don't really have to worry about, since we're not doing that here. But it says we're going to, if we're going to do this for a regular channel, what we're going to do is we're going to set this start for this conversion. I don't think I have. So here, that's this AD start. We're going to set the start in the conversion for the control register, and then we have to have the channel selected in the sequence register. That's what's right here. And then once it's done, the result will be stored in the data register. And how do we know it's done? The end of conversion flag will be set after conversion. And if we've used interrupts, what would happen is that end of conversion flag would be set, and then immediately it would go into this interrupt execution of some code. Since we're not doing that, we're just going to sit there and monitor that end of conversion flag, and once that's done, we know that the conversion has been finished. Okay, for our intents and purposes in this lab, we're just doing a single conversion, so we're not going to need to do all this other stuff for the single channel continuous mode. We may want to do it multiple times, but we're not really necessarily thinking about it that way. But what you see in this particular slide is that the scan, if we want to do single channel continuous, the continuous bit in ADC CR2 has to be 1, whereas scan in both of the single channel conversions is set to 0. But when we go to the scan mode with single or scan mode with continuous, scan is 1 in both of those, continuous is 0 in the single mode scan, and scan mode for continuous is 1. And again, I think this will be clear after you do it, but the main thing is you need to know where your data comes from the analog to digital converter into, and that for us is the data register for ADC And so for us, since we're trying to do just a simple single conversion into ACD N5, which is port PA0, remember, sort of strange, it's port A0 gets moved into channel 5, then it says, okay, what do we need to do? Well, it says that you can see we're putting in here this exclusive OR with 14. What does that mean? Well, let's look. Okay, so we see that we want in the sequence register this value, but why? Where is that coming from? Well, we know that it's exclusive OR, as I said. So we have this, and I'm just going to focus on these three hexadecimal digits. And so we have 0, so that's going to be 0, 0, 0, 0. 4, that is 0, 1, 0, 0. And then the rest are zeros. Okay, the only really thing I need to look at are these, because nothing else has changed. Okay, this SQ1, SQ2, SQ3, SQ4, that corresponds to the, if you're doing a scan mode, like which groups of channels do you want to actually convert. So you can see it says SQ1 4 to 0, it says first conversion in regular sequence. These bits are written by software with the channel number 0 to 18 assigned as the first in the regular conversion sequence. So this is the first channel that's going to get converted. Well, we want to convert what's on PA0, which is channel 5. So what did I do? And I think I said, let me make sure I didn't even put the right number in there. So here is 0, here is 4, then I need to put 1, and I didn't. I should have extended it to there. Okay, so that makes better sense because there's that 1. Okay, so what that meant though is I put, let's erase and see, I put in this SQ1 0 to 4, I put 00101. Well, what's that number? That number itself is 5. So in SQ1, I basically put the number 5. Why? Because I'm trying to convert channel 5. Okay, that's why that's chosen. So if I wanted to convert channel 1, then I would have that. If I wanted to convert channel 8, I would do that. So that the channel that you want to convert is what needs to be put in that SQ1 register. So anyways, and then the next thing it says is, okay, I put in zeros here, which means L3 to 0 is just 0. What's that mean? It means I'm going to do just one conversion. If I wanted to do 2 conversions, I could do 0001, so forth. So it says, this is what we're basically it's saying, how many conversions are we doing, and what channels do I need to convert. And if I do multiple channels, then I can put the other channels in SQ2, SQ3, and SQ4. So that's how you get it to choose which channel you're going to do the conversion on. And then the next step is, okay, we got to get ready for the conversions. It says, once we've set up, turned off deep power down, and we've done the voltage regulator, the analog to digital converter can be enabled, and we have to wait a certain length of time, and we have to enable the clocks, and it says, Then we have to enable the analog to digital converter, and it says that the flag analog to digital ready will be set once the ADC is ready for conversion. Okay, so that's a flag that you could watch, and of course that basically will tell you when this stability time has been passed. It says AD disable, or AD dis equals 1, disables the analog to digital converter, and says ADEN and ADDIS are then automatically cleared by hardware as soon as the analog to digital converter is effectively disabled. So we've talked about all that. It talks about looking at this interrupt service routine register, which we can do, but we're not really doing that part. The main thing that we have to do is we have to look at this, for us, the end of conversion flag. If you're using injected channels, you would need to look at this one. And so here's that ADR DY, so that's the bit that will tell you about whether or not the AD converter is ready to go. And remember, we have the AD start and JAD start to start the conversion. Okay, so you can see that what this is giving you little sections to talk about waiting for the AD start, disabling the ADC converter, and then waiting for the A to D enable. It's just giving you ways to do that here with simplistic sort of while statements. And you can see here, for example, the A to D to enable, it's comparing the control register with 1. Okay, here's the control register and the bits, and it's ANDing it with 1. Well, 1 is putting a 1 in that digit right there. And it's saying, okay, if that ANDed with 1 is not equal to 0, then keep going through it. So if it is equal to 1, or if it is equal to 0, then exit out. And so that's what happens once it enables. Then it will, wait. Once it has been enabled, then everything will be okay, and it would exit out for that. Here's disabling the analog to digital converter. So notice it does the same thing as it did before. It says if this control register ANDed with 1 is equal to 1, so if I AND it and we AND it with this 1, so if this bit had been a 1, it would be equal to 1. Then it's going to go into here. Then it's going to say exclusive OR with 2. 2 is 1, 0. So it's going to say put a 1 in that bit. Boom. It's going to disable the analog to digital converter. So anyways, that's what this setup does right there. And then wait for AD start and JAD start equals 0. That what's going on here is, okay, it's looking again at the this, and it's saying look at AND it with C. Well, C, what is C? C is the number A is 10, B is 11, C is 12, so that's going to be 8 and 4, so that's going to be 0, 1, 1, no, 1, 1, 0, 0, so 8, 4, and then nothing for the other 2 bits. So this is 1, 1, 0, 0. So it's ANDing the control register with that number, and so when those go 0, then it's going to exit out of that while loop. So here's sort of the full setup code for the analog to digital conversion. And you can see here it's talking about here it just talks about this as the initialization. So if you call that particular initialization for the analog to digital converter, that if you call this routine, it's going to set up the clock enable. Here we see we're enabling GPIO port A. Here we're saying we're going to configure port A0 as an analog input, and we're going to turn on the analog switch so that that goes to analog to digital channel 5. And so, okay, now we're going to turn on the chip. Now we're going to enable the regulator. So this is that deep power down mode. This is that AD voltage regulator. And then we're going to set the clock mode. Then it says, okay, now what are we going to do? We're going to configure the channel for a single conversion of this. We already talked about that. We're going to enable the analog to digital converter. Notice it's going to clear that ADR DY bit. So that's right there. Then we're going to enable the analog to digital converter, and it says, okay, put the 1 there. And then here's this while loop that's looking at 1 and that, and it's saying, okay, oops. While that is equal to 0, then it's going to sit there in that loop. So we're looking at that 80 ready bit. And then here you see again, we're clearing the 80 ready bit again. And it says, hey, we're just enabling the regulator lights to turn off when you clear that 80 ready bit. So that's just, silliness that's coming over here. And then how do we actually make a reading? So then you're going to see the next part is, okay, we have to set the 80 start bit, and that's this bit here, and we have to wait for it to go back to a 0. And when it does go back to 0, so we set it, then when it goes back to 0, that says, oh, it's been converted. Then we can read from this data register. And then you can do something with it. So again, that's the whole point of all of this, is we set the AD start, we watch it. Once it's been watched and it goes back to 0, we can read the value. So that's the key thing that you have to look at is in here, this is all just sort of enabling for one channel conversion. And then, see, all of this is done in this analog to digital converter initialization setup. So you don't even have to fool with any of that, really. That's all doing channel 5 from port A0. Now, if you wanted to change which one it was doing, you would have to go change that function. But anyways, we have to tell it here that we're going to look at, so you can see in here it gets exclusive ORed with 4, so we're telling it to start. Then we're going to AND it with this 4, which is this. And so when it ANDs, while it's 1, so it's going to continue going through the loop, when it finishes, that means that it got converted to a 0 right there. It's done. We can read the data register and get a number from it. Okay, so here's some just simple questions that I thought I would ask and you could look at and think about and make sure you sort of get the idea behind. But suppose you have an audio sampling system that operates at 96 kilosamples per second with 16 bits per sample. Okay, well, it says, so this is a little bit different. What's the data rate per channel? Okay, well, we've got 96,000 samples per second times 16 bits per sample. That gives us the data rate. It says, what's the highest frequency that could be sampled? Well, obviously, if we're doing 96,000, we expect that we can't have anything higher than half that and be that the frequency. So 48 kilohertz is the highest frequency. And it says, okay, well, what if we had a 10 megabit per second channel or connector? Well, this is one channel right here, this 96,000 times 16 bits. So we'd have to take how many megabits per second is that, and then say, okay, that turns out to be, let me make sure I do it right in my calculator. So 96,000 samples per second times 16 bits. So that's 1.536 megabits per second. And that's just for a single channel. So if I have 10 of those, or 10 megabits per second channel, I can say 10 divided by that and so that's gives me, if I did it, if you could have a non-integer value, I got 6.5104. So I can have 6 channels. If I had to have 7 channels, it would go over the 10 megabits per second, and I wouldn't be able to do it. Okay, so then let's talk just a little bit more about what would happen if I want to go through and do what we're going to do in the lab, which is actually sample something. We're going to use our temperature sensor, which is an LM34. It's just a simple temperature sensor. We're going to use it in this package here, which basically has 3 leads to it. Now notice that the way it shows it to you, notice this flat back. If you look at the pins coming up at you looking at your face, the ground pin is going to be the right one as long as you have that flat part at the back side. And then the voltage that you're going to look at, Vs, the supply voltage that you're going to apply 5 volts to, there is Vs, it's on the left, and then the voltage that you're going to sample, V out, that's a function of the temperature, is the middle one. Now remember, when you flip the actual LM34 over and down and put it into your board, make sure you put it into 3 separate spots on the board, or you're going to have, don't put them all in 3 spots that are actually connected all together. Put them in 3 different rows so that you don't have that problem where those are connected. Vs, I don't think your board has 5 volts on it anywhere, so you probably need to use the 5 volts from the DC power supplies that are in there, and Jitendra can help you with that. That's not very hard, but just take the 5 volts to somewhere on one of the buses, or take it to that there. But they're similar to the DC supplies that you've used in circuits lab, so that shouldn't be a big deal. So you're going to want to tie this lead to 5 volts, tie this to ground, and now make sure you tie the common lead of the 5 volt source to the ground on the board that you're using, because this ground should be the ground of the board, but you also want to tie the 2 together so that way you get the right 5 volts there. Now notice, it does say that you could have this Vs. It says you could have it be from 5 to 30 volts, I think. Maybe it's 20. Yeah, maybe it's 20. So you could have that high voltage, but you need to have at least 5. So the reason I say you probably should use the power supply is because of that. If you use just the 3 volts or so that's on your board, it'll probably work okay, but not as good as it should. And what happens is the output of this sensor is basically simply giving you 10 millivolts per every degree Fahrenheit. So if, for example, it was 10 degrees Fahrenheit, then you would read 100 millivolts, not milliwatts. I don't know where that came from. So just be aware that that's going on here. Okay, so yeah, here it is. V out is plus 10 millivolts per degree Fahrenheit. So you're going to use this, and what it says to do, and this is just to get you a little bit of a difference to make sure you know what you're doing. It says at first you want to look at pin 2 and enable that on your analog to digital converter input. Now pin 2 is not what we did. We did pin A0. So pin A2 we're going to have to go way back. Oops. And remember, we want to do pin A2. So what's the difference? We're going to have to look at ADC 7. So that channel 7, not channel 5. And you have to set up the sequence register to do the right thing. And then it says display the voltage on the LCD. Okay, that sounds more complicated than it is, but if you look at it, it's sort of already set up in the template to use the LCD controller, so you don't have to worry too bad about that. Okay, then it says you're going to connect the LM34 temperature sensor to pin A2. Okay, so at first you're not actually using that sensor, but then you're going to connect it to sensor A2, so then you should get whatever the voltage is that corresponds to the room temperature, which should be, that room is always sort of the ice dome, so maybe it's just 65 degrees in there, so 65 degrees times 10 millivolts per degree is going to be 650 millivolts. So you'd expect something like that to be read. And so then it will display that temperature in degrees Fahrenheit. So you have to just convert so simply from the voltage that you read, which is basically going to be a binary number, into this temperature to get it displayed. So you have to look at this code here for how to display something and just see how to modify it a little bit. And then the last thing you have to do is just modify this code to display the degrees in Celsius when one of the push buttons is pressed. So again, just trying to get you to use something else to get a little bit more comfortable with the GPIO ports. You're going to use a joystick button, click it. When you click it, it should modify from being in Fahrenheit on the LCD screen to in Celsius on the LCD screen. That's really a super simple part. It may take a little bit more programming than you think, but it's just a little programmatic difference, with the formula using the conversion from Fahrenheit to Celsius, which relates to that 5/9 times T minus whatever if you have it in Fahrenheit. So just use that standard formula that you've seen before, manipulate it to be able to put it into the appropriate form on the LCD. So that's it for this lab. There's really not a whole lot going on that you have to do and totally understand in the lab because most of it's done for you. But the big thing is just looking at what you need to set the sequence register to, set the analog switch control register to, and so forth to make sure you're doing analog to digital, port A2 and analog to digital channel 7. So, and then reading those voltages and manipulating it a little bit. All right, hope that sounds good, and I will finish this video and put it up on YouTube.